It is here, but I don't know where to do it. He wants to put full screen on the screen. Okay. 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 Yes, you see it on YouTube? She does. She sees it. Okay. Now we should wait 1 minute. We start exactly at the hour, right? Imagine. Yeah. It's yeah. Yeah. Yes. Test the sound again. You want to see? It works? Okay, thanks. And it's 2. So we should start. Okay, I'll start my timer. So hi, everybody. My name is Viola, and I'm very excited to be here today with you in Toulouse and with all the people connected to talk about gravitational waves. I've been given the honor and the burden to introduce the gravitational waves to you. So I would like to talk to you about fundamental interactions, and in particular gravity. And so what are those gravitational waves? And then I'll talk a bit about what are the sources that we can observe. Then I will really focus on how we detect them. And for these, after a short historical introduction, I will really focus on the current ground-based network of detectors, which are interferometers, for which I will describe the detection principle and the design, then describe how we reconstruct the signal, and then what are we sensitive to. Okay, so in the table, you have our current understanding of fundamental interactions. You can think of them as the basic forces through which particles or objects can affect each other. They are the strong interaction, which is responsible for nuclear forces, electromagnetic interaction, responsible for phenomena related to light, electricity, or magnetism, the weak interaction that we see in action for radioactivity, and gravitation, which, as you know, is responsible for apples falling from trees and for the motion of the planets and galaxies. So in the third column, I try to show you how strong these interactions are. I do this with this relative strength. It is relative to the strong force. This is why the value is 1 for the strong force. And what these numbers are telling you is that typically the electromagnetic interaction will be 100 times weaker than the strong force. The weak interaction 1 million times weaker. And if you look at gravitation, this number is extremely small. So it's 0 followed by 37 zeros and then a 1. Of course, these are order of magnitudes. So gravitation is the weakest interactions of all fundamental interactions. And I have a simple sketch there to tell you how you should interpret these numbers. How do we get to numbers like this? So let's imagine we take 2 protons at a given distance. That protons will feel a repulsive interaction because they are charged. And this force will be described by this red formula, where Q is the charges. So Q1 times Q2 is the electron charge square. D is the distance, and K is the Coulomb constant. But the protons also have a mass, so they will also attract each other through gravitational interaction. And this is described by the blue formula, where M are the masses and G is the gravitational constant. So if you calculate these 2 forces, you will realize that the repulsive one is much stronger than the blue one. So if you make the ratio between the 2 values, this is where you will get these very small numbers. So this ratio will be 10 to the minus 36, which is the relative between gravitation and electromagnetic. So gravitation is much weaker. This is not so far away from everyday's experience. You have the typical example the example of the metal paper clip, that stands on the table because of gravity, but then it's enough to have a tiny magnet to pull it up. So tiny fridge magnet wins over planet Earth, which is surprising somehow. So gravity is practically negligible at particle level. This is also why it is hard for us to constrain it precisely in, for example, in the lab on particle physics experiments. But one thing about gravity is that imagine you're building an atom, you keep adding charged particles, but they are charged plus and minus. So in the end, the atom is neutral. And you don't have that with gravity. Gravity always adds up because you only have the mass. You don't have a plus or minus charge. So gravity dominates when masses are big. And so naturally, we tend to dominate at large cosmic scales. Gravity is also special conceptually in the way we describe it, while the other fundamental interactions are described in a common mathematical framework, the quantum field theories. So they're described as exchange of particles. Gravity is described by general relativity. So it really stems out of the space geometry. And finally, if really I need to convince you that gravity is super interesting to study, it is through gravitational effects that we have observational evidence of some of the big mysteries that modern physics is trying to solve, like dark matter and dark energy. So our current understanding of gravity is based on this theory from the early 1900s from Albert Einstein, the general relativity. So although in our everyday life, the space, three-dimensional space and time might seem different objects, in relativity, space and time are tightly connected and must be treated together. So they are actually 4 coordinates of a 4-dimensional continuum where all physical events happen. And this is the what we call the space-time. So in general relativity, the space-time geometry is related to its matter content. And this is where gravity comes from. And this is shown in this formula. This is called Einstein's field equation. We don't have to go through the details of the formula, but you notice there are these objects with 2 indices. These are tensors. It's like a generalization of matrices. And each Greek index can take the 4 values of the 4 coordinates of space-time. And on the left, you have something that describes the curvature, so a geometrical property of the space-time. And on the right, you have this other tensor that describes its content in terms of mass and energy. This is often depicted or illustrated as an analogy. In this drawing, you see the space-time is illustrated by this kind of 2-dimensional net. And the fact that the Earth is there, a big mass will generate some curvature. So objects are attracted towards the Earth, not because of a force in the sense of an exchange of a particle, but because they are following the most natural path in the space-time. They're kind of falling. Of course, it's just an analogy. And gravity is weak. In these terms, you can think of the space-time as being very rigid, so you need big masses to deform it. And you see there is a proportionality constant, so gravity is weak can also mean this constant is small, quote unquote. So like 1 year after finalizing this theory, Einstein wrote a paper where he showed that these equations in the weak field approximation can allow solutions that mathematically look like waves. So these are waves of the space-time curvature propagating in the space-time. So it took some decades to the scientific community to converge on the understanding that these waves are a real effect that we can measure, and this is why we are here talking about it. And so indeed, systems with accelerating masses can radiate gravitational energy and generate waves in the space-time curvature. This is shown in this small animation. This is a typical system we will discuss more later, but you have 2 objects orbiting around each other. They lose energy by emitting gravitational waves and they get closer. And so again, in this analogy of this net is kind of an analogy to the space-time, these waves propagate. The waves propagate at the speed of light. And now what we have to ask ourselves if we want to detect them is, what effect do they make that I can measure? So this is shown by this other animation on the right. So all these points on this sort of net are masses. You have to think of them as masses that feel gravitation, but are not subject to any other force. So they would move in the space-time in the most natural way. We call this free fall, masses in free fall. So if a gravitational wave passes through this tube, it will cause the space to stretch in one direction while shrinking in the other with this pattern that is oscillating. So the observable effect that we are going to focus on today is that if you take any two test masses that are in free fall, their relative distance will oscillate in time. So this delta L, the length of the distance divided by L, is directly proportional to what I call here H, which is the typical amplitude of the wave. So if we find a way to measure this, the relative distance oscillations of two free-falling test masses, then we are directly sensitive to the amplitude of the waves. We'll see what that means. Let me first, before I go to detection, let me first talk about sources. So the gravitational waves are just a messenger. It's exactly like light, and the universe is full of them. And as light, they can have different frequencies, and gravitational waves of different frequencies will come from different sources, which means if I study different frequencies, I will study different physical phenomena. Also, different frequencies will require different experimental strategies. So typically, this is what is called the gravitational wave spectrum plot. You see the frequency increases from left to right, and you see that you have a possible emission of gravitational waves in all of the spectrum. You go from very low frequency, where gravitational waves from the early universe might have left an imprint in the cosmic microwave background in its polarization, to the nanohertz region, that we try to study with instruments that monitor pulsars. Pulsars are highly rapidly rotating neutron stars that work as super precise clocks. So you probably have heard in 2023, these experiments have announced their first evidence of possible gravitational waves coming from the superposition of many signals from supermassive black hole binaries. Then we go to the millihertz scale, which is a region that will be explored by the future experiment LISA that you will also hear about in this workshop, until we get to the high frequency, let's say around from 10 to 10 hertz to 1 kilohertz, which is the one you will focus on during this workshop. This is the region of the frequency that is explored by the current network of ground-based detectors. So these are the LIGO, Virgo, and Cagra detector, which I will also call the LBK. And please allow me to do so, but after we will introduce them very precisely. So what are the kind of sources, gravitational wave sources, that we can see in the LBK? Typically, we divide them in 4 big categories. The first source is binary system of compact objects. Is the animation we had before. What is a compact object in this context? Is either a black hole or a neutron star. We are talking about masses between 1 and let's say 100 times the mass of the sun. These systems are in an orbit, and they, I hope you can hear me despite the noise, and they lose energy by emitting gravitational waves, and they get closer and closer. Another source is irregularity on pulsars. So these rapidly spinning neutron stars, if they have, for example, a small mountain or a dip on their surface, these may emit gravitational waves, and we can be sensitive to those. Other stellar explosions, like supernovae explosion, would also emit gravitational waves. And finally, instead of looking at single event, we can also see if there is a kind of diffuse background of gravitational waves that could come from the superposition of many individual events that are too far away to be seen independently, but that eventually in the dreams could also contain itself some component from an early universe. So in this workshop, you will focus on the first kind of systems, but please remember that in the LBK, we search for all of those. So narrowing it down to this binary system that we also call compact binary coalescences, or CBC. These are were supposed to be among the loudest expected sources of gravitational waves for the LBK. You have here a simulation. Again, these are two objects orbiting around each other until they get to a merger. And then you can also see in the simulation how gravitational waves, the gravitational wave signal goes in all the universe, and then eventually comes to Earth, and we see it. So indeed, all confirmed observation by the LBK are today of this nature. So this is also why we focus on those. And they are special because we can calculate precisely what kind of signal we would see. And as you will see in the lectures by Tito and then Quentin, knowing what signal you look for makes a big difference in your ability to find it. So how does this signal look like? You see it here. So this is time on the x-axis, the plot on the bottom left, and then you have the strain. This strain is the name we give to this relative distance difference. It's like delta L over L. And so while the system orbit around each other, this is an oscillating signal, and you see that its frequency increases and its amplitude increases up to the merger where you have the maximum. So there is a very active scientific community that works on calculating these waveforms. You use different strategies. In the inspiral part, you use some analytical expansion, while you do need numerical relativity at the merger, close to the merger. And you have some methods to put them all together and then to treat the ring down of the final objects will be created and a bit excited. So one thing is it's super nice to know which signal you're looking for because you're much more sensitive, but this makes you really model dependent. So if you look for something very precise, you might end up finding only this. So it is super important that we include as much physics as we can in these waveforms. And this is really the job of this big community. So in your tutorials, number 2, I think you will play with waveforms. You will see there is a simple line of code, and then you call a waveform. They have fancy names, there are families, there is a big community behind that builds these waveforms. And so it seems easy, but it actually has a lot of work behind it. There is a bit delay. Okay, so now to how do we detect the signals? I just want to mention super quickly that actually the first efforts to detect gravitational waves were taking a different path than what we have today, and were focused on what are now resonant bars. These are big metallic cylinders that would resonate at specific. Wow, I'm not sharing anymore. Pause. We don't see the slides anymore. Ah, c'est juste ça? C'est le code. C'est bizarre parce que quand we should check that we are still sharing with Zoom. Sorry, technical problem, but nobody can know because we are not on Zoom. Stop my timer. C'est Zoom qui a craqué. Bon, c'est pas grave, on se reconnecte. No, we are not on Zoom, and we kicked this computer out of Zoom. Someone writes that we have a. How do we? Okay, sorry for people watching the video. If the video exists, we have a technical problem, but we will be right back. Matthew is going to fix everything. Yes. No, I don't touch anything. I wait for you. Sotto. Later. Are you sure the whole still this one? Yes, exactly. I was here. You were paying attention. That's good. So are we? And now we are back live, Joe. So we were live all the time. Okay, good. So sorry, everybody. Technical problem as you know. As usual, I just wanted to mention that the first detection efforts. Sorry, I restart my timer. The first detection efforts were focusing on this idea of having resonant detectors. I don't want to discuss them. I just want you to know that they existed. There is an historical picture here from the first experimental setup, but actually there were many experiments following this. But in the end, this was not a successful strategy. So these detectors don't exist anymore, although the idea of using resonant systems is still on the table. The detectors that really got us the first detection are interferometers. So this is what I'm talking about starting from now. The first prototypes started in the 70s, and the construction started in the 90s. Between these two dates, there was a big boost in this field, which was thanks to an indirect observational evidence of gravitational waves. Indeed, recently discovered pulsar was seen to be orbiting around another object, and this orbit was observed to decay. So the two objects were getting closer. And in the plot on the bottom left, the red points are telling you how we measure the objects to get closer. And then the black curve, or blue curve maybe, is telling you how the objects are expected to get closer if they lose energy because of gravitational waves, according to Einstein's general relativity. So you see that the emission of gravitational waves and the general relativity describes very well the observation. Now, this is not a direct detection yet, but it was a strong indirect support. And this is what we have today. This is a worldwide network of interferometers. You have 2 in the Americas, 2 in Europe, 1 in Japan, and 1 in India, which construction is soon to be started. So in the workshop, the workshop is organized by the LBK. This is LIGO, Virgo, Cagra. So you will really focus on the ones that are in red. This is how they look like. This is how they look like. This is LIGO Hanford, Virgo, LIGO Livingston, and Cagra. Cagra is underground, so this is not a real picture. And again, these are working together in a network that we call the LBK. So what is the timeline, typical timeline? I said the construction started in the 90s for LIGO, first one LIGO, then the other than Virgo. The first runs were in the years 2000, but in this configuration, the detectors were not sensitive enough. They were working, but not sensitive enough. And they were not expected to be sensitive enough. Cagra construction started a bit late. Then the LIGO and Virgo got upgraded to what we call the advanced detectors. And so the first advanced LIGO observing run was in 2015. This brought us the first direct detection of a gravitational wave signal coming from a merger of 2 black holes. Virgo joined in 2017, and this run brought us the first detection of a gravitational wave signal coming from two neutron stars merger, a neutron star merger, and this was also the first multi-messenger observation with gravitational waves. I know you will have a talk. Frédéric is going to talk about this event. And Cagra joined a bit later. This is also summarized in this timeline. You see the different observing periods that are called O, like observing. And we are here now. So we have just finished, the LBK has just finished the longest joint observing campaign. And our data, as Agatha is going to explain later, are made public after a proprietary period. So at the moment, you have the data from the first third of this 04 that is public. And so we already have around about 200 confirmed signals overall. And so many more are to come. Now the detectors are offline. We are installing some additional improvements. So expect them to be online soon and to take a lot more data and to make a lot more observation in the next years, until eventually our infrastructures will become obsolete. So this is when we will have to move to a new infrastructure. This is what we call the 3rd generation ground-based detectors that John will talk about on the last day of the workshop. And again, we will also explore other wavelengths with, for example, LISA. Okay, so the basic detection principle. These objects are giant Michelson interferometers. What does that mean? You have a laser that gets split in 2, and you have 2 arms. There is a mirror at the end of the arms. The laser goes there, comes back, and then the 2 half of the beams get combined again. So you know that because of the wavy nature of light, light plus light is not always more light because waves can interfere. So if you're completely off phase, light plus light can actually be darkness. And this is where these interferometers work. We say they work on the dark fringe. It means they put themselves in a configuration of completely disruptive interference, so that on my photodiode, the transmitted power is null. Actually, we don't really work at the minimum, but we are close to the minimum because it's more convenient to understand the response of the detector so that it is linear. This is also shown by this video in a very simplified way. You have the laser, these are the two arms, and this is the photodiode. And this is the exaggerated passing by of a gravitational wave that will cause the relative length of the two arms to change. And so the interference pattern I will record will inform me about the gravitational waves. The video is also highlighting that they work on the dark fringe. You see there is no transmitted power in their normal position. And then when a gravitational wave passes by, it will cause the length of an arm to vary with respect to the other. So on my photodiode, I will see a pattern. And especially for CBCs, I know which pattern I expect. So I can recognize this kind of signals. Okay, now connecting the drawings to the pictures you saw before, all this part, the laser, the photodiode, this beam splitter, and actually we will see we have mirrors also at the beginning of the arms. This is all in the central building. This is a picture of the Hanford site. In this talk, I will show some pictures. These detectors are not all exactly the same. In particular, Virgo and Kagra made some different choices, technological choices with respect to the two LIGOs that look very similar. So, but for my talk, let's assume they're all the same and just focus on the basic concepts because they are the same. Then the solutions might differ a bit. So you see these big tunnels that are not tunnels because they're on the surface, but these are the arms. So inside you have a big vacuum pipe and the laser travels in it. And then 4 kilometers at the end of this arm, you will have a mirror. So I told you that the transmitted power I can measure here is proportional to delta L over L, so to what we call the strain, but this will evolve in time. So actually what we do is that we measure the transmitted power very often with a high sampling frequency. So what you will work with, the data you will work with is actually a time series. You will also have tutorials about time series. So we often say h of t. And I also told you that, okay, there is a gravitational wave passing by, the relative distance will change, so I will see a strain in my detector appearing here. But what I didn't tell you is there are many other effects that can either induce a real motion of the mirrors or affect the way I measure my optical signal here. And this we generally call noise. So if you look at the strain you measure from your interferometer, this will be the sum of the noise plus eventually and hopefully a gravitational wave. So one typical thing that moves the mirror is the ground motion. Okay, so we want to isolate the mirrors from the what we call seismic noise. So we do this with, so again, these pictures are for Virgo. Let's just focus on the general concept. We want to isolate the mirrors from the ground. So the mirror is this small thing here. And we do this with this series of inverted penduli that will attenuate the seismic noise starting from a given frequency. So if you go to the end of the arm in the Virgo detector, you will see these big 8 meters high towers. And inside you have the suspension systems. And the mirror is this small thing at the bottom. You see a picture of one mirror from the initial Virgo run, and you see it's transparent, which might be confusing, but this is because our laser is not in the visible wavelength. So the laser is 1 micrometer. So please trust me that these mirrors are perfectly reflective for this wavelength. So the mirrors here, so the aim of the game is that these mirrors here don't feel any force in the direction of the beam. So you remember I told you we have 1 mirror at the beginning of the arm, 1 mirror at the end. So these mirrors are acting as free fall test masses in the direction of the beam. Of course, not in the other 2 directions where they cannot really move. And so these are my free fall test masses between which I'm trying to measure this relative difference of distance. So I just have a couple of slides just to tell you that my these are kilometer long Michelson interferometer idea is really not correct. These objects are much more complex. I won't go through their complexity, also because I'm not an expert. But just if you look at publications, for example, they have the simplified drawings, and the simplified drawings look like this. So you see, it's much more complicated than just the Michelson interferometer. Let me just highlight some of the differences. So all of the arms are equipped with Fabry-Perot cavities. What does that mean? It means that, so I told you that this strain is proportional to delta L over L. So one way to get to a strain that is small, because the typical strain gravitational wave strain we were targeting is of 10 to the minus 21. This is very small. One easy way is to have longer arms. No, our arms are already 4 kilometers long, but what we do is that we actually make the light go forth and back many times, so that we don't measure delta L over L, but delta L over an effective length of the arm. So this allows us to go a bit lower in sensitivity. Another thing you might notice all detectors have is a power recycling power recycling cavity, power recycling mirror again. So, and this is, since just a small fraction of the light is transmitted, this object re-injects all the reflected power into the arms. And this helps us because high laser power will help me mitigate some noise I get in the readout of the photodiode at the end. Of course, high laser power has other problems, but then we try to be smart also there. And finally, one thing I also want to mention is that you can see this object signal recycling. So this is something that wants to amplify especially the signal, so we can see it much better. And you have many other. You see there is some cleaning in the input and, sorry, you see, okay, input and output laser. We also use squeezing of light. Sometimes the squeezing depends on the frequency. So please keep in mind the Michelson interferometer idea, but just remember it's much more complicated than that. Another thing that is wrong in the video I showed you with the two mirrors moving a lot is that interferometers are not passive detectors. They're actually actively controlled all the time, so that they never go too far away from their operating point, which you remember is very close to the complete disruptive interference. We say that interferometers are locked when they are there. So how do we do that? Well, we move the mirrors. We have small actuators on the mirrors that can push them and attenuate any movement. So any output power variation is attenuated. We do that with something that's called a control system. It's just a loop. It's very similar to what active noise canceling headphones do. So you measure a variation in the transmitted power, then you send the control signal to the mirror actuators that tries to attenuate them. It pushes the mirrors. So the problem is a gravitational wave signal, which would move the mirrors, will be attenuated as well. Not would be, will be, is. And the thing is that our control signal, however, contains the information of what the mirror movement would have been. The control signal knows how much we push the mirror. So in the end, the quantity, the signal is reconstructed from the transmitted power. This is the part of the power that my control system didn't manage to attenuate, plus the control signal. Okay, and this is what we call reconstruction. Now I told you, okay, the reconstructed strain is the sum of the two, but look, this is read on a photodiode, this is an electrical signal, so these are electrical signals. And I'm telling you, I'm actually measuring a delta L over L. So how do I get from the volts to the meters? Or actually, it's relative. So how do I convert this signal to the actual displacement? And this is called calibration. And the idea is very simple. It's I generate a known displacement of the end mirrors, and then I see what I get. How do I generate a known displacement? There is no student that goes and pushes the mirrors, of course, but I have a laser. It's behind the mirror. It's another laser. And this laser, the photons of these lasers push the mirrors in a controlled way. And this allows us to calibrate. So this is called the photon calibrator. This calibration happens all the time and doesn't disturb the measurements. For the moment in Virgo, only in Virgo, we also have another calibrator called the Newtonian calibrator. where we have moving masses near the mirrors to generate a non-gravitational force, and then we see what happens in the signal we read. So today, well, these 3 days, you will work with reconstructed and calibrated strain from real data and from simulated data. So I promise you that the reconstruction and calibration team have done a perfect job. And so your strain is perfect. However, perfect does not exist. So what the calibration teams do in real life is they also provide data that quantify how good my calibration was, and they monitor this over time, and also how accurate, in which uncertainty you can trust it. So this is what is called calibration bias and uncertainty. You will not play with those, but you will see, for example, parameter estimation. Just be aware that when we run parameter estimation on real events, parameter estimation has to know about that. Okay, so I am at I think the last part, and I have 10 minutes, which is great. How sensitive are our detectors? So I already told you that the strain we see is the sum of the noise plus the signal, and our job is to extract a tiny signal from the noise. So it's very important to know the noise of your detector. And if someone asks you what's the noise of your detector, this is typically what you will provide: the amplitude spectral density. The formula is here, is the square root of this Sn of f. This Sn is the power spectral density, or PSD. Remember the PSD, you will play with the PSD. Here I'm showing you the square root of it because it's more convenient for me, because this is directly proportional, comparable to characteristic strains, but it's just a square. It's not a big deal. So the amplitude spectral density looks like this. These plots, these are modeled signal, is theoretical curves. How should you read these plots? For each frequency, the curve is telling you how much strain, how much signal I will see in my photodiode that is just coming from noise. So the lower this curve, the more sensitive is my detector. Typically, if the spectral density does not depend on the frequency, we say this is white noise. You might know about white noise, and this is not the case, as you will see. You also see there are several sources that sum up. And then a hypothesis that we do often is that the noise is stationary. It means that if you look at the noise at any time, it will be a bit different, but this will all be realization of the same underlying curve, which also means if you want to determine the PSD of your data, you can average over time. And you will use PSDs to generate noise in your tutorial, so you will do this firsthand. I think Kanta is going to talk a bit about how we model noise. I just wanted to mention to you the main sources of noise. At high frequency, you have the shot noise. We met this already. This is why we want a high laser power. This is how well I can read out the light because of fluctuations in the photon's arrival time on my photodiode. At medium to low frequency, I have this radiation pressure noise. This is another quantum noise. And these are fluctuations in the force that the photons in the big laser in the arms exert on the mirror, how strong they push the mirror, and they also fluctuate. Then you remember I told you the mirrors are isolated from seismic noise, starting from a given frequency. You see that the seismic noise goes up like crazy at very low frequency. And then you can have some noise coming from thermal microscopic movement of atoms, for example, in your coatings, which are the reflective part of the mirrors, or in the suspensions that suspend the mirror. So it's complicated. And it is just a theory. If you compare this with the characteristic strain, this is how it looks like. This is characteristic strain from O3. So you see that the general shape is well described by this theoretical expectation, but you also see there are a lot more features. So some of these features are understood, some of them are unavoidable, like mechanical resonances of the systems. Some of them are understood but complicated, like noise coming from scattered light. And some of them we're really just trying to figure them out. So this is a job that is called noise hunting. It's super important. Francesco will talk about it. And so the point to remember is these interferometers are beautiful experiments. The day you build an interferometer, this will have some limitation in sensitivity, but still there is a lot you can gain by getting to know the interferometer well. You not only want to build it, you also want to understand everything that can shake it somehow. And so this is what the detector characterization and commissioning people do, and it's a super important job. In this plot, you also see these numbers, megaparsecs in parentheses. This is another proxy for the detector sensitivity. It's called the BNS range. It's a distance at which, if binary neutron star coalescence occurred, the detector would be able to see it on average well enough. And so if someone asks you, how sensitive is your detector or the detector you want to build, typically either you show a curve like this, or if you just want to give one number, you give this number. So the lower the curve, the more sensitive, the higher the number, the more sensitive the detector. Okay, I want to say something about your amplitude spectral density and the fact that it really shapes how the signals will look like. I think Frédéric will also touch upon this, so I will be quick. I just want to say this is another way of looking at CBC waveforms. In this case, is as a function of frequency. Remember h of t. I made a Fourier transform of this object. You will also play with Fourier transforms, I think, maybe even today or tomorrow. And so I go in the frequency space and I take the modulus, the absolute value. And you see that these are CBCs with different masses, low masses to high masses of the two compact objects. So the shape is always the same. There is this power law function part, which is related to the inspiral. These systems spend most of their life in the inspiral phase. And then you have this kind of knee for the merger and ring down. So imagine now you put your PSD there. It does like this. So you're sensitive between 10 and 1 kilohertz. You will right away see that, for example, you will be sensitive to the inspiral part of a BNS, of a low mass system, but maybe sensitive only to the merger of this other very massive system. So this is what you see also here, yet another thing you will play with. These are omega scans. This is the frequency. This is the time on the Y and X axis. And the color is giving you kind of normalized signal amplitude that you see in the data. So a CBC signal, you remember, would increase in frequency over time. So it goes up and increase in amplitude. So look at I just wanted you to look at the time scale. So this signal is visible for 30 seconds. This is a real signal, a low mass. And this signal, which is a typical vanilla BBH, 2 BBHs of 30 solar masses, is visible for a fraction of seconds. So you hear LBK people saying, yeah, but BBHs are short signals. This is just that they get in our sensitivity band at the very end of their lives, okay? So these guys have been orbiting around each other for millions to billions of years, okay? We just see them in a different moment of their life. So this is why the BNS will last longer. And by the way, I'm going back to this gravitational wave spectrum. This is exactly the same thing when you say you need different instruments to probe different physics. This same plot is this colorful plot, and the other colorful plots are showing other sources. So massive binaries, stochastic background from supermassive binaries, and in black you have the PSDs. So the lower the PSD, the more sources you will see. But see, this is LIGO Virgo, this is the third generation. Even with the third generation, you will not be sensitive to this. Okay, so all these instruments are complementary. We need all of them. LISA and the Einstein telescope will do different physics. They will meet at some point, so they can talk to each other, but they're really complementary. Okay, I think this is my second to last slide. 5 minutes, which is perfect. And you remember I told you that the noise is stationary, and then what you will do in one of the tutorials is you have a PSD, so you have a curve like this, and then you will ask your library to generate some noise. What this will do is that for each frequency, it takes the PSD as the average value and then generates some Gaussian noise. Different realizations. Now, in real life, there is what is called glitches. This is non-stationary noise. You recognize here some omega scans with some famous glitches in them. So these are this big, amount of power at some point in the detector with different shapes. And so this non-stationary noise is something that complicates a bit the picture. And this is typically the topics that are studied by the detector characterization people. And this is what also Francesco is going to show. These glitches are annoying because, first of all, you can think it's a signal in some cases. Oh, a very loud signal. Why it was of a it was coming from a data quality issue. And sometimes they can overlap over signals. So this is a famous plot. This is still the binary neutron star detection from 2017. You can recognize, I hope, the waveform behind, so the typical shape of a CBC. And you see that this was initially hidden by a big data quality issue, by a big glitch that we had to mitigate after. So your PSD will describe this. The PSD will describe all the fluctuations with the blue and the green, but it's not going to give you this. This you have to, it's something that nature adds. So you have to understand where they're coming from and possibly mitigate them. Okay, I'm already at my conclusion slide. So what conclusions, maybe it's a start because it's the start of the workshop for you, but from the prediction in the beginning of 1900 to the first detection almost 100 years later, gravitational waves are now routinely observed by the LBK. We had like one event every 2 days on average during the fourth observing run, and it was very exciting. They probe phenomena that were invisible until we managed to detect gravitational waves, like coalescing black holes or neutron stars. And they're really complementary to electromagnetic astronomy. The gravitational wave spectrum spans from the early universe to stellar mass binaries, and the different frequencies will reveal different physics and different epochs of our universe. And experimentally, I think this is just the beginning of an era, because I told you the LVK detectors are being improved, so we will have increased sensitivity. But you heard also about the results from the pulsar timing arrays. Those people keep collecting data, so looking forward to their new results. We have future missions like LISA that will explore a frequency band that is still unexplored, and we have plans for next generation ground-based detector. So in the future, we will really be able to explore more widely the whole spectrum, and also more deeply, because our detectors will be more sensitive. So in this workshop, you will explore the methods behind these discoveries and use both simulated and real LBK data, which I think is super exciting. So my final comment is I hope you will have fun. Thank you. Sorry for the Nico.
Thank you, Yola, for this amazing talk and being on time, despite the little glitch in the presentation.
Glitches everywhere.
Before I ask you for a question, there is a question online that I will read to you, Viola. Be ready. So Mehdi Helbouatuti, sorry for the pronunciation, asks, in slide 13, I noticed that the Hanford noise is consistently, although slightly higher than the Livingston one. Is the reason understood?
So slide 30, probably. Sorry, I went to 13. Yes, thanks for this. Thanks for the question. And I think the fact that you're asking this question means that you now are able to read PSDs, which is great. Sorry, amplitude spectral density. This is exactly the kind of information you can get. And indeed, this is what they are saying is that you can see that, especially at some given frequencies, some detectors are more or less sensitive than the others. You notice clearly Virgo, starting from frequencies less sensitive, and also Livingston is more sensitive than Hanford, a low frequency. And I don't think we have so the two LIGO detectors, I believe it was the other way around in the previous run. In 04, this is still the case, that Livingston is more sensitive. And I think this is really, so the two detectors are the same. So I think this is really related to the understanding of the noise. There are some infrastructural choices that are a bit different in the two. I know, for example, the cooling is a bit different in Livingston, but I think the big difference is how well we understand these detectors. But maybe Francesco as a detector.
Yes.
And if you want to go talk more about it should work.
Try.
People from both French. Okay. Okay. So speaking, share. LIGO detectors. rocky desert, which plays at about microseismic noise. Noise of the activities. So more or less, this is the story of why a little bit more noise at low frequency.
I think they did not hear you very well online.
Okay. Can you?
Detector character. One difference between the two LIGOs that are built the same, but it's the site. So in particular, the LIGO in a desert in the Washington state, and while the seismic noises right. So there is also the choice of the site. And if it's the same, the choice of the site can. Any question here?
So apparently the sound is not super great online. Well, we'll do our best. Can you?
Answering the question before, comment by a detector position expert. But and I hope you can hear me. I hope you can hear me now. So we had a comment by a detector characterization expert. Francesco is going to give a talk, and he was mentioning that although the two LIGO detectors are exactly the same, the site is completely different. So in the case of LIGO Hanford, there is more seismic noise, especially at low frequencies, that is causing some especially angular noise. So this is also why the sensitivities are different. I hope this was heard.
Yes, now they where everybody was able to answer hear the answer. So you heard it 3 times. That's great for you.
Tomorrow you should ask during your talk.
Okay. There is another question online. Rowan AP asks, are there any measurable effects on time due to gravitational wave? Is that accounted for?
And that's a very good point. So as I said, in relativity, time and space are tightly go together. You have to treat them together. So in the passing of a gravitational wave will affect time as well, although in a less evident manner to show. So what we base our detection principle with the interferometers is really the effect on space, on relative distances. And so no, we don't take into account the effect on time. This effect exists. I am not aware of any hope to detect it somehow, but I might just be ignorant if anyone else wants to comment. But you are right that the effect we look at, the observable, is involving the space.
Well, that's a great program for future detectors then. Okay, any question here in the amphitheater?
Thank you for, can you hear me? Yes. Thank you for the nice talk. You said that signals are seen for a very short time in gravitational wave detectors due to the sensitivity of the frequency range we're looking at, basically. But these phenomena are intrinsically short, or is it simply due to the limitations of the way we are observing the signal itself?
Thank you. So it depends what you mean by this phenomena. So this binary system, let's focus on the CBCs. This is, my point here was to show that how we see, so that our sensitivity depends, what you see in your detector is a convolution of the physical system you're observing and what your detector is seeing. So in case of CBCs, these objects orbit around each other for millions of years, and they will always emit gravitational waves. And why, even during the spiral, and this is why they get closer to each other. Now, the merger itself is a short let's say, happens over a short period. But for example, in the case of the BNS, if I'm sensitive between 10 and, I don't know, 1 kilo, 10 hertz and 1 kilohertz, I will see the in spiral. And they spend a lot of time in the in spiral. So this is why my BNS signal will be longer. So it doesn't mean that the actual life of the physical system is longer. It means that they enter in our sensitivity band at the moment where they have more time to live. While we had I don't know if you see, we had the detection, it's called GW231123, very, very massive system. And for this one, we had like 3 cycles in band. The system, the signal was super short. That there is a publication, I'm sure Frederic will talk about it. So in case of very massive system, you probably will just see the merger. For the BNS, the merger is too far away. I would like to see the merger and study the physics, but it's not there yet. More than that, I'm eating the microphone.
Maybe like
Sorry, it was inaudible. So the answer is that no, the real life of these systems is very long. And when we see, so the fact that we see a shorter signal for BBHs, so binary black holes, than we see for BNS is just due to the moment of their life when they enter our sensitivity band. So I guess to answer your question directly, no, it's not intrinsically different. It depends on my detector. And some of them, very, very high massive black hole binaries, I just don't see them. I have to wait for Lisa. So yeah.
Okay. Well, there are other questions online, but I think it's time to end this talk. Thank you again. Thank you for the great questions, and we'll see you soon for the next talk. Oui, je pense que c'est un problème.